Analytics for bivariate data. Part 1. In Part 1, we will consider the case in which both the variables are quantitative in nature. So when we have two columns of data for some entities, we have bivariate data. The two columns may be both quantitative or both qualitative or one quantitative and one qualitative. In this lesson, we will learn how to perform some analytics with bivariate data when both the variables are quantitative in nature. So let's look at an example of bivariate data where both the variables are quantitative in nature. In this example, the first column is order ID. This is a label column and not a data column. We have two data columns, both are quantitative. One is quantity ordered and the other is order amount. The order amount is in dollars and the quantity ordered is in units. So what kind of analytics can we perform here? Remember, through analytics, we want to tell a story. We want to find some interesting and relevant things hidden in data, things that can help us in making decisions to improve things. So when we have two columns of quantitative data, we can do the following things. We can compute the covariance and correlation between the two variables. We can plot a scatter diagram to visually look at the type of relationship between the two variables. We can perform regression analysis to get a mathematical equation that captures the relationship between the two variables mathematically. And if the units of the two columns are different, like in this example, we can plot what is called a dual axis chart that shows how the two variables behave relative to each other. So let's first talk about covariance and correlation for our example. So covariance and correlation are mathematical measures of relationship between two quantitative variables. In Excel, we can use the covar function to compute the covariance between two arrays of quantitative data. We can also use the correl function in Excel to compute the correlation between two arrays of quantitative data. Once we have those values, we can then interpret the values of covariance and correlation. So let's talk about covariance first. So covariance is one of the measures of relationship between the two variables. The covariance value can be negative, it can be 0, or it can be positive. A positive value of covariance implies a positive relationship, whereas a negative value implies a negative relationship. A value of 0 implies no relationship between the two variables. So what's a positive relationship? A positive relationship implies that if the value of one variable increases, the value of the other variable also increases. And if the value of one variable decreases, the value of the other also decreases. A negative relationship, on the other hand, implies that if the value of one variable increases, the value of the other variable decreases, and vice versa. Now, the magnitude of covariance has no interpretation. Variance may range from extremely large negative values to extremely large positive values. The value of variance really depends on the units of data used. So for the data on the right, the covariance comes out to be 531.96, which implies a positive relationship. And we use the covar function to compute this value. So all we can say looking at this value is that the relationship is positive. Why? Because the sign is positive. We cannot make any statement about the strength of the relationship. By looking at this value, we cannot say that the relationship is very strong or weak or whatever. So for that, we have correlation, which we will study on the next slide. Correlation is the other measure of relationship between two quantitative variables. Just like covariance, a positive correlation value implies a positive relationship, while a negative value implies a negative relationship, and a 0 correlation value implies no relationship. Now, correlation can vary only between -1 and +1, unlike covariance where there are no limits. A correlation value of +1 implies a perfect positive relationship. That means it cannot get any stronger. It's perfect. Similarly, a correlation value of -1 implies a perfect negative relationship. A correlation value of 0.9 or higher implies a very strong positive relationship. Between 0.7 and 0.9 roughly, the relationship is considered strong positive, not very strong. Between 0.4 and 0.7 roughly, the relationship is considered moderate positive. Between 0.2 and 0.4, the relationship is considered weak positive. Between 0.001 and 0.2, the relationship is considered very weak but positive. Likewise, for negative ranges, negative 0.7 to negative 0.9, the relationship is considered strong negative, and so on. So these cutoffs for strong, moderate, weak, etc. are approximate and not set in stone. Again, the correlation value of 0 implies no relationship. So for the data on the right, we get a correlation value of 0.938, which implies a very strong positive relationship. And we use the Correl function to compute the correlation. Scatter diagram or scatter plot. When we have two quantitative variables, we can draw what is called a scatter plot or a scatter diagram. It provides a visualization of the relationship between two quantitative variables. We try to put the independent variable on the x-axis and the dependent variable on the y-axis. If we cannot tell which is the independent and which is the dependent variable, we may arbitrarily put one variable on the x-axis and the other on the y-axis. In this case, clearly the order amount depends on the quantity ordered. Of course, it also depends on price. But if we just have these two variables, then clearly quantity ordered is the independent variable which determines the order amount. Now, on a scatter plot, if the data points, which here are shown in red, if they're going from bottom left to top right, which is the case in this picture, the relationship is positive. Why? Because if the value on the x-axis is increasing, the value on the y-axis is also increasing, and that's a positive relationship. Now, if the data points are going from top left to bottom right, the relationship is negative. Why? Because as the value on the x-axis is increasing, the value on the y-axis is decreasing. So in our example, we can say that the relationship is positive. How can we say if the relationship is strong or very strong or weak or moderate? We'll look at that on the next slide. Regression analysis. So on a scatter plot, we can add a trend line. The trend line is shown here in light pink. It's also called the regression line. It's also called the best fit line. It's also called the least square line. It has lots of names. And we can also get a mathematical equation of the trend line. In our example, the mathematical equation of the trend line is y equal to 182.28 times x plus 14.457. So y is the y-axis variable, in this case order amount, and x is the independent variable, in this case quantity ordered. So this equation is also called the regression equation, and we can rewrite this equation in terms of our variables. Order amount equal to 14.457 plus 182.28 times quantity ordered. Using this equation, we can estimate the order amount given a value of quantity ordered. Now, if the data points are close to the trend line throughout the chart, the relationship is considered strong. So closer the points to the trend line, stronger the relationship. Now, if all the data points fall exactly on the trend line with no deviation, the relationship is considered perfect, and the correlation value for such a scenario would be 1. If the data points are away from the trend line, the relationship is considered weak. Further away the points go, the weaker the relationship gets. There's a lot more to regression than what we have covered here on one slide. Dual axis chart. If the units of the two quantitative variables are different, like in our example, we can draw what is called a dual axis chart. In a dual axis chart, we have two y-axes, one for each quantitative variable, drawn on different scales, different units. So in our example, quantity ordered is in units, whereas order amount is in dollars. So here's a dual axis chart. Notice it has two y-axes. One on the left, quantity ordered, one on the right, order amount. Quantity ordered is shown by columns. So these are quantity ordered, and we are using this scale 2, 4, 6, 8, 10. Order amount is an orange line and is drawn on the scale on the right. Order amount, that's the scale in dollars. So on a dual axis chart, we can visually see if both the values are rising and falling at the same time. If they are, then there's a positive relationship between them. So in our example, we see that both the variables are rising and falling together. Hence, we can say that the two variables are positively related to each other. So this concludes the lesson on analytics for bivariate variables with both quantitative variables.